Hey guys, and welcome to some more AP Physics C Major Derivations. Today we're going to be doing the velocity as a function of time for a sphere or any object that is falling, that is in free fall when a force of drag is applied to it, like air resistance, which is the force drag. So let's just jump right into it. So what we want is velocity as a function of time, right? And normally, maybe if you took AP Physics 1, you might be thinking, well, I know that there's V equals AT, or V naught plus AT, whatever. V equals V naught plus AT, and I can derive that from there, right? Now you could be thinking this, but this is the thing, you need the acceleration, which is constantly changing, because if the velocity is changing, then guess what? Acceleration is also changing. Sorry, not if the velocity is changing, the acceleration is changing. Well, the reason the acceleration is changing is because initially when you drop the ball, it has little to no velocity, just acceleration, and then it'll keep increasing its velocity, which hence changes the drag force. Hence, by Newton's second law, it'll change the acceleration. So, if we're already thinking about Newton's second law, we should start with Newton's second law. Whenever you have derive a differential equation, um, usually when you're deriving a something as a function of time, you're going to want to start with Newton's second law. And if that doesn't work, then you're going to have to go through something else. But for the drag force, you always want to start with Newton's second law. So let's sum the forces in the y direction. Let's think. We see our free body diagram here already. So we have force drag. Actually, no. Always call your direction of acceleration to be your positive. So we're going to say force gravity minus force drag is equal to mass times acceleration by Newton's second law, right? So now let's just sub in. If I know the mass is m, well, Fg is mg, and the force drag is bv, where b is a positive constant. We call that the drag coefficient, is equal to ma. And you might be thinking, okay, well, where does the differential equation come into play here? I'm about to show you. This is where it comes into play. Mg minus bv is equal to m, and a is the derivative of velocity, which is dv dt. Now I have a differential equation with dv dt, meaning I can solve for v as a function of time. But I want to simplify this a little bit more, so I'll divide both sides by m, right? And I'll get g minus bv divided by m is equal to dv dt. Now this is a separable differential equation. So we're going to go ahead and separate our variables by multiplying dt to both sides. And we're going to divide both sides by g minus bv over m. G minus bv over m. And that's going to cancel these on this side, and it's going to cancel dt on this side, and we're going to get dt is equal to 1 over g minus b over m v dv. And now this is a separated differential equation that I can now just integrate, that is bad, integrate both sides. And you might be thinking, okay, well, you're going to get plus c here, and that's a lot of work. Do we have to do that? The answer is no, because if I can just adjust my integration bounds by thinking, okay, well, I'm going to go from time equals 0 to some arbitrary time t, you're allowed to do that, right? And I'm going to go from, well, at time t equals 0, what's the velocity? Well, the velocity would be 0, right? And at time t equals t, well, the velocity will be some function, some velocity v of t. So I'm just going to call that v. Well, it's better to work with v of t. But in your actual derivations, just work with v there and then turn it into v of t at the end. Actually, no, I'm going to show you that. Just we'll put v there, where v stands for v as a function of time. So the left side will integrate to t from 0 to t, and the right side, now we need to think. Well, you might be thinking, this looks like ln, but I don't want to jump through all the loopholes of, well, you don't have to, because there's this identity in calculus that they might not give you on the equation sheet, but this is something you should definitely remember. If you're taking calculus BC, this is also great to remember. If I have the integral from, we'll just do the indefinite integral. The indefinite integral of, let's say, a x plus b dx. That integral will evaluate to 1 over a ln ax plus b. Oh, ax plus b and plus c, of course. So now if I can think, well, what is this integral? What's my ax? Well, this looks a little bit like ax plus b. It's just minus. And I have x and dx, and I have v and dv. So I'll just transform this a little bit so you guys see more what I'm talking about. this is going to be negative b over m v plus g dx. Oh, not dx, dv. So these two are the same integrals. I just move things around a little bit. So, well, what's our a in this situation? Well, our a can be positive or negative, and in this situation, it's negative b over m. So this integral, guess what? It will evaluate to 1 over, well, 1 over negative b over m, negative b over m, ln of negative b, oops, negative b over m v plus g from the bounds of integration from 0 to v. And on this left side, I'll just evaluate this t minus 0. And now this looks a little bit easier, right? Because I use that calculus identity, it's a lot easier to work with. So now I'm just gonna fix this left side. T minus 0 is just t, and this whole thing, I'm gonna put this in parentheses because I can just take out my constant after I've integrated. This whole thing will turn into negative m over b, because if I multiply m to both sides, right? These two cancel and I'll get negative m over b. And now I'll evaluate that natural log. So we'll do ln negative b over m, and I'm going to plug in v here. You might be thinking, shouldn't we use a dummy variable? You could. It's really up to you. Like in this situation, you could have used v of t because you have dv, and you want to get v of t. I'm just using v just for simplicity. I don't want to write v of t all over and over again. It's easier to write v. But it's really up to you. So then I have that. And now fundamental theorem of calculus minus, and now if I plug in 0 for v, then I'll just get ln g. So now this looks a little bit easier, but we're going to go to the next page to continue this. So now, in order to get rid of this pesky multiplier, I'm just going to give it to the other side. So it's negative, by multiplying this entire thing by negative b over m, the reciprocal, which will cancel this and turn it into 1. So negative bt over m is equal to ln, and I'm just going to go back, g minus b over m v minus ln g. So that looks a little bit easier to work with. And now if you can remember your properties of logarithms, the properties of logarithms is ln a minus ln b. A and b are just arbitrary numbers, whatever it is, or anything, is equal to ln a divided by b. Ln divided by b. So now here we're just going to go through and we're going to turn that into one natural log. We're going to g minus b over m v divided by g. Now that's one natural log, but I don't want to have the natural log there. I want v as a function of time, and this is my v as a function of time right now. Like I said earlier, I'm just writing it as v for simplicity. So I'm going to isolate that v by just doing some algebra. So in order to cancel that ln, I'll raise both of these sides to e, and now I get e to the negative bt over m is equal to g minus b over m v. And now I have g here again. So now I'm just going to multiply by g to both sides because I'm going to get closer and closer to what's it called? To isolating v of t. So now I have g e to the negative bt over m is equal to, and these g's will cancel, so I'll just get g minus b over m v. Okay, this is starting to look a little bit easier, but I want a positive v of t. So what I'm going to do is I'm just going to add b over m times v to both sides. And now this looks a little bit something like this. And if you're saying, well, a lot of these steps I could just skip by doing it in my head, of course you can. And if you can, that's great. I'm just doing them on screen. So for simplicity, so we don't miss anything, right? So you can see all the steps the first time. But I definitely recommend skipping some steps as you keep going and just doing multiple steps in one. But now I see that I want to get b of, or v alone, so I'll subtract by ge to the negative bt over m on both sides. And this is looking way more consolidated. I'm close to getting v by itself because now I just have a constant multiplier. But I want to factor this left side so it looks kind of neat. So now I have g, 1 minus e to the negative bt over m equals b over m v. And now I'm going to say I'm going to multiply by m over b to both sides to get v by itself, because these will cancel. mg divided by b, 1 minus e to the negative bt over m, is equal to v as a function of time. And that is all we needed from this. So yeah, hopefully this helped you guys. Hopefully you got what you needed out of this. But yeah, if there's also a little bit, there's a small tiny extra thing that I want to show. So if we go back to the original differential, sum forces is equal to Fg minus Bv, or no, we'll just write it how it is. Mg minus Bv equals Ma. When this sphere eventually reaches terminal velocity, assuming it's falling and it won't hit the ground until a very long time, the terminal velocity means that the velocity will not change. So if the velocity isn't changing, dv dt is 0, and therefore a is 0. So that means the sum forces will be 0, because m times 0 is, well, 0 equals 0. And now if I solve for v terminal, I get mg over b, right? And what does that look like? That looks like what we had up here. So basically, this v of t equation is v terminal 1 minus e to the negative bt over m. And that makes sense, because if I plot this on a graph, it will look a little bit something like this. So it'll start at 0, and then it'll flatten out at this v terminal, because we'll call that, sorry, we'll call that v terminal, because at that v terminal, as t approaches infinity, right, e will go e to the negative infinity, which is 1 over e to the infinity, which is 1 over infinity, which is 0. So this entire term will go to 0, and this v of t will evaluate to v terminal. And that makes sense, because as you have infinite time, the velocity will be constant, right? The forces will be balanced. But that's just one other thing that I wanted to show you guys, and hopefully this helped out. Hopefully it made some more sense. But yeah, I'm excited to see if you guys enjoyed it. Please let me know if there's anything I missed. And as always, good luck on your exams, and I'll see you guys in the next video.